This chapter is about OCloud and its key concepts. Here we have the ORAN overall architecture, and this is the placement of the OCloud in it. Today, we will start with what is OCloud, its architecture and key concepts, and its deployment scenarios. In the traditional approach, telecommunication operators were required to purchase application software and hardware from the same vendor. For instance, vendor A would provide RAN software that could only run on their specific hardware. So, the telecom operator has to buy software and the respective hardware from the same vendor. However, with the shift towards a cloud-native world of applications, applications can now run as virtualized networks or containerized network functions on hardware from different vendors. This decoupling of applications from the underlying cloud layer and hardware results in three distinct layers. The first layer is the application layer, which includes RAN applications. The second layer is the cloud layer, which can be Kubernetes or OpenStack, providing the necessary infrastructure. The final layer is the hardware layer, including FPGA cards, CPU, GPU, memory and other components, which can be sourced from various vendors. This decoupling empowers telco operators to optimize their networks and negotiate with different vendors. By having the freedom to choose the best software and hardware components from different sources, telcos can achieve better efficiency and cost savings. So, here the O-RAN alliances comes into picture, and focus on RAN flexibility, deployment velocity, and the cost reduction through cloud architectures, which allows telco operators to decouple application software, cloud and the hardware into different layers, opening up new possibilities for optimizing and negotiating with different vendors. This not only benefits operators, but also to the vendors, where it gives opportunity to more than one vendor in the ecosystem, reducing the monopoly of only few big players. Now, let's start with what is OCloud, or the cloud platform. The cloud platform is a set of hardware and software components that provide the cloud computing capabilities to execute RAN network functions. The RAN network functions are shown as ODU, OCU in this diagram. The cloud platform hardware includes compute, networking and storage components, and may also include various acceleration technologies required by the RAN network functions to meet their performance objectives. An example of a cloud platform is an OpenStack or a Kubernetes deployment on a set of general-purpose servers, including FPGA and GPU cards, interconnected by a spine or leaf networking fabric. Key characteristics of OCloud architecture are, starting from decoupling of hardware from software. This aims to improve flexibility and choice for operators by decoupling selection and deployment of hardware infrastructure from software selection. Standardization of hardware specifications across software implementations, to simplify physical deployment and maintenance. This aims to promote the availability of a multitude of software implementation choices for a given hardware configuration. Sharing of hardware. This aims to promote the availability of a multitude of hardware implementation choices for a given software implementation. Flexible instantiation and lifecycle management through orchestration automation. This aims to reduce deployment and ongoing maintenance costs by promoting simplification and automation throughout the hardware and software lifecycle. Now, let's talk about management aspects of the OCloud. Since service management and orchestration, or simply the SMO, is the central management entity as per the O-RAN architecture, it talks to the OCloud over the O2 interface. The O2 interface is a collection of services, and their associated interfaces that are provided by the OCloud platform to the SMO. First is the Infrastructure Management Services, or simply IMS, which is responsible for deploying and managing cloud infrastructure. IMS talks to 4COM component of the SMO over the O2-IMS interface. IMS takes care of cloud installation, its inventory, fault management, performance management aspects. So, if a new cloud resource or resource pool has to be created, 4COM interacts with IMS over the O2-IMS interfaces and requests for new cloud instance creation. and internally, IMS takes care of instance creations. Second is Deployment Management Services, or simply DMS, which are responsible for managing the lifecycle of virtualized or containerized deployments on the cloud infrastructure. In short, DMS takes care of workload placement on the cloud. For examples, deployment of an application on the cloud instance, termination of the application, scaling, healing, health check, and similar many other such operations are performed over the O2-DMS interface. If you see in this diagram, there is only a single instance of IMS per OCloud, and there are many DMS instances. Here, IMS is a single tool which takes care of multiple cloud cluster creations, such as Kubernetes clusters, and whereas DMS is equivalent to Kubernetes API server endpoint in each cluster. Means, if you want to deploy an application on a specific Kubernetes cluster, then we have to find respective DMS entity from the IMS inventory, and NFO will request the application deployment to that specific DMS. Now, let's see the monitoring aspects of the OCloud. If you see, in terms of resources, OCloud has IMS resources, which are hardware components, such as servers, switches. Then there are cloud DMS resources, like Kubernetes pods, deployments. And then there are applications, like RAN network functions deployed on top of the OCloud. These all resources uses the respective interfaces to send their fault and performance data to the SMO, as shown in this diagram. So, this part covers the management and orchestration of the OCloud, with the help of IMS and DMS components of the OCloud. Now, let's talk about Edge Cloud and its deployment scenarios. In traditional telecom operators, cloud was only at central station. With the new booming use cases and requirements, like online gaming, connected cars, drones and high bandwidth applications, there is a requirement of the cloud near the users. Edge cloud refers to the extension of cloud computing resources and services closer to the network edge, bringing computation and storage capabilities closer to where data is generated and consumed. In terms of deployment, the location of the edge cloud, it can be very close to the user, or little far, or at regional level. Depending upon the type of use case and specific requirements, it can be deployed at respective distance from the radio units. It enables low latency, high bandwidth, and real-time processing, which is crucial for emerging applications like Internet of Things, augmented reality, autonomous vehicle and high-speed processing. So, ORAN has proposed various deployment scenarios for the edge cloud. If you see this diagram, ORAN has categorized the deployment scenarios as A, B, and likewise up to scenario F. Like in scenario A, OCU, ODU, and near RT-RIC are deployed at regional level edge cloud, and connected to the radio unit. On the other hand, in scenario C, ODU is deployed very close to the radio unit, on different edge cloud, while OCU and near RT-RIC are deployed at regional level edge cloud. By deploying edge cloud at the DU level, closer to the radio access network, data processing and storage can be performed at the edge, reducing latency and improving network efficiency. The O-RAN Alliance recognizes the importance of edge cloud in achieving its goals of RAN flexibility and cost reduction. By leveraging edge cloud in their deployments, O-RAN members can enable advanced applications, deliver better user experiences, and pave the way for the future of telecommunications. This section covers the edge cloud and its deployment scenarios.